James Hopwood Jeans. The mathematical theory of electricity and magnetism. The three divisions of electromagnetism. 1. The fact that a piece of amber, on being rubbed, attracted to itself other small bodies, was known to the Greeks, the discovery of this fact being attributed to Thales of Miletus. A second fact, namely, that a certain mineral or lodestone possessed the property of attracting iron, is mentioned by Lucretius. These two facts have formed the basis from which the modern science of electromagnetism has grown. It has been found that the two phenomena are not isolated, but are insignificant units in a vast and intricate series of phenomena. To study, and as far as possible interpret, these phenomena is the province of electromagnetism. And the mathematical development of the subject must aim at bringing as large a number of the phenomena as possible within the power of exact mathematical treatment. 2. The first great branch of the science of electromagnetism is known as electrostatics. The second branch is commonly spoken of as magnetism, but is more accurately described as magnetostatics. We may say that electrostatics has been developed from the single property of amber already mentioned, and that magnetostatics has been developed from the single property of the lodestone. These two branches of electromagnetism deal solely with states of rest, not with motion or changes of state, and are therefore concerned only with phenomena which can be described as statical. The developments of the two statical branches of electromagnetism, namely electrostatics and magnetostatics, are entirely independent of one another. The science of electrostatics could have been developed if the properties of the lodestone had never been discovered. And similarly, the science of magnetostatics could have been developed without any knowledge of the properties of amber. The third branch of electromagnetism, namely, electrodynamics, deals with the motion of electricity and magnetism. And it is in the development of this branch that we first find that the two groups of phenomena of electricity and magnetism are related to one another. The relation is a reciprocal relation. It is found that magnets in motion produce the same effects as electricity at rest, while electricity in motion produces the same effects as magnets at rest. The third division of electromagnetism, then, connects the two former divisions of electrostatics and magnetostatics, and is in a sense symmetrically placed with regard to them. Perhaps we may compare the whole structure of electromagnetism to an arch made of three stones. The two side stones can be placed in position independently, either in any way resting on the other, but the third cannot be placed in position until the two side stones are securely fixed. The third stone rests equally on the two other stones and forms a connection between them. 3. In the present book, these three divisions will be developed in the order in which they have been mentioned. The mathematical theory will be identical, as regards the underlying physical ideas, with that given by Maxwell in his treatise on electricity and magnetism, and in his various published papers. The principal peculiarity which distinguished Maxwell's mathematical treatment from that of all writers who had preceded him was his insistence on Faraday's conception of the energy as residing in the medium. On this view, the forces acting on electrified or magnetized bodies do not form the whole system of forces in action, but serve only to reveal to us the presence of a vastly more intricate system of forces, which act at every point of the ether by which the material bodies are surrounded. It is only through the presence of matter that such a system of forces can become perceptible to human observation. So that we have to try to construct the whole system of forces from no data except those given by the resultant effect of the forces on matter, where matter is present. As might be expected, these data are not sufficient to give us full and definite knowledge of the system of ethereal forces. A great number of systems of ethereal forces could be constructed, each of which would produce the same effects on matter as are observed. Of these systems, however, a single one seems so very much more probable than any of the others, that it was unhesitatingly adopted both by Maxwell and by Faraday, and has been followed by all subsequent workers at the subject. 4. As soon as the step is once made of attributing the mechanical forces acting on matter to a system of forces acting throughout the whole ether, a further physical development is made not only possible but also necessary. A stress in the ether may be supposed to represent either an electric or a magnetic force, but cannot be both. Faraday supposed a stress in the ether to be identical with electrostatic force, and the accuracy of this view has been confirmed by all subsequent investigations. There is now no possibility, in this scheme of the universe, of regarding magnetostatic forces as evidence of simple stresses in the ether. It has, however, been said that magnetostatic forces are found to be produced by the motion of electric charges. Now, if electric charges at rest produce simple stresses in the ether, the motion of electric charges must be accompanied by changes in the stresses in the ether. It is now possible to identify magnetostatic force with change in the system of stresses in the ether. This interpretation of magnetic force forms an essential part of Maxwell's theory. If we compare the ether to an elastic material medium, we may say that the electric forces must be interpreted as the statical pressures and strains in the medium, which accompany the compression, dilatation or displacement of the medium, while magnetic forces must be interpreted as the pressures and strains in the medium caused by the motion and momentum of the medium. Thus, electrostatic energy must be regarded as the potential energy of the medium, while magnetic energy is regarded as kinetic energy. Maxwell has shown that the whole series of electric and magnetic phenomena may without inconsistency be interpreted as phenomena produced by the motion of a medium, this motion being in conformity with the laws of dynamics. More recently, Larmor has shown how an imaginary medium can actually be constructed, which shall produce all these phenomena by its motion. The question now arises, if magnetostatic forces are interpreted as motion of the medium, what properties are we to assign to the magnetic bodies from which these magnetostatic forces originate? An answer suggested by Ampere and Weber needs but little modification to represent the answer to which modern investigations have led. Recent experimental researches show that all matter must be supposed to consist, either partially or entirely, of electric charges. This being so, the kinetic theory of matter tells us that these charges will possess a certain amount of motion. Everything leads us to suppose that all magnetic phenomena can be explained by the motion of these charges. If the motion of the charges is governed by a regularity of a certain kind, the body as a whole will show magnetic properties. If this regularity does not obtain, the magnetic forces produced by the motions of the individual charges will on the whole neutralize one another, and the body will appear to be non-magnetic. Thus, on this view, the electricity and magnetism, which at first sight appeared to exist independently in the universe, are resolved into electricity alone. Electricity and magnetism become electricity at rest and electricity in motion. This discovery of the ultimate identity of electricity and magnetism is by no means the last word of the science of electromagnetism. As far back as the time of Maxwell and Faraday, it was recognized that the forces at work in chemical phenomena must be regarded largely, if not entirely, as electrical forces. Later, Maxwell showed light to be an electromagnetic phenomenon, so that the whole science of optics became a branch of electromagnetism. A still more modern view attributes all material phenomena to the action of forces which are in their nature identical with those of electricity and magnetism. Indeed, modern physics tends to regard the universe as a continuous ocean of ether, in which material bodies are represented merely as peculiarities in the ether formation. The study of the forces in this ether must therefore embrace the dynamics of the whole universe. The study of these forces is best approached through the study of the forces of electrostatics and magnetostatics, but does not end until all material phenomena have been discussed from the point of view of ether forces. In one sense, then, it may be said that the science of electromagnetism deals with the whole material universe. Chapter 1. Physical Principles. The Fundamental Conceptions of Electrostatics. State of electrification of a body. 5. We proceed to a discussion of the fundamental conceptions which form the basis of electrostatics. The first of these is that of a state of electrification of a body. When a piece of amber has been rubbed so that it attracts small bodies to itself, we say that it is in a state of electrification, or, more shortly, that it is electrified. Other bodies besides amber possess the power of attracting small bodies after being rubbed, and are therefore susceptible of electrification. Indeed, it is found that all bodies possess this property, although it is less easily recognized in the case of most bodies than in the case of amber. For instance, a brass rod with a glass handle, if rubbed on a piece of silk or cloth, will show the power to a marked degree. The electrification here resides in the brass. As will be explained immediately, the interposition of glass or some similar substance between the brass and the hand is necessary in order that the brass may retain its power for a sufficient time to enable us to observe it. If we hold the instrument by the brass rod and rub the glass handle, we find that the same power is acquired by the glass. Conductors and insulators. 6. Let us now suppose that we hold the electrified brass rod in one hand by its glass handle, and that we touch it with the other hand. We find that after touching it, its power of attracting small bodies will have completely disappeared. If we immerse it in a stream of water or pass it through a flame, we find the same result. If, on the other hand, we touch it with a piece of silk or a rod of glass, or stand it in a current of air, we find that its power of attracting small bodies remains unimpaired, at any rate for a time. It appears therefore that the human body, a flame or water, have the power of destroying the electrification of the brass rod when placed in contact with it, while silk and glass and air do not possess this property. It is for this reason that in handling the electrified brass rod, the substance in direct contact with the brass has been supposed to be glass and not the hand. In this way we arrive at the idea of dividing all substances into two classes according as they do or do not remove the electrification when touching the electrified body. The class which remove the electrification are called conductors, for as we shall see later, they conduct the electrification away from the electrified body rather than destroy it altogether. The class which allow the electrified body to retain its electrification are called non-conductors or insulators. The classification of bodies into conductors and insulators appears to have been first discovered by Stephen Gray. At the same time, it must be explained that the difference between insulators and conductors is one of degree only. If our electrified brass rod were left standing for a week in contact only with the air surrounding it and the glass of its handle, we should find it hard to detect traces of electrification after this time. The electrification would have been conducted away by the air and the glass. So also if we had been able to immerse the rod in a flame for a billionth of a second only, we might have found that it retained considerable traces of electrification. It is therefore more logical to speak of good conductors and bad conductors than to speak of conductors and insulators. Nevertheless, the difference between a good and a bad conductor is so enormous that for our present purpose we need hardly take into account the feeble conducting power of a bad conductor, and may without serious inconsistency speak of a bad conductor as an insulator. There is, of course, nothing to prevent us imagining an ideal substance which has no conducting power at all. It will often simplify the argument to imagine such a substance, although we cannot realize it in nature. It may be mentioned here that of all substances the metals are by very much the best conductors. Next come solutions of salts and acids, and lastly as very bad conductors come oils, waxes, silk, glass and such substances as scaling wax, shellac, india rubber. Gases under ordinary conditions are good insulators. Indeed, it is worth noticing that if this had not been so, we should probably never have become acquainted with electric phenomena at all. For all electricity would be carried away by conduction through the air as soon as it was generated. Flames, however, conduct well, and for reasons which will be explained later, all gases become good conductors when in the presence of radium or of so-called radioactive substances. Distilled water is an almost perfect insulator, but any other sample of water will contain impurities which generally cause it to conduct tolerably well. And hence a wet body is generally a bad insulator. So also an electrified body suspended in air loses its electrification much more rapidly in damp weather than in dry, owing to conduction by water particles in the air. When the body is in contact with insulators only, it is said to be insulated. The insulation is said to be good when the electrified body retains its electrification for a long interval of time, and is said to be poor when the electrification disappears rapidly. Good insulation will enable a body to retain most of its electrification for some days, while with poor insulation the electrification will last only for a few minutes or seconds.